Hi, so this is a quick whistle-stop tour through the one-dimensional echocardiographic measurements taken from murine or rat hearts using the VisualSonics VEVO770 high-resolution ultrasound system. This is a technology that allows high-resolution recording of ultrasound images from rodents with very high frequency and high sample accuracy. Of course, it's only as accurate as the measurements taken. What I'm showing you here is a quick tour around the one-dimensional analysis, which basically looks at single points through the heart and measures wall thicknesses and lumen volumes, and really should only be used when comparing phenotypes of normal, undiseased animals. So if you've got a disease model like an infarction or a hypertrophic myocardium or some sort of congenital defect that leads to left ventricular abnormalities, you've got to be very careful about using this one-dimensional analysis, because you may be missing some very important physiology, which those of you who understand about cardiac physiology will realize the importance of that when you see the data analysis that we're using. But if you're just comparing normal mice, this is quite a quick way of getting some data to be able to look and see how these mice compare, certainly in terms of average wall thicknesses, lumen sizes, and function. So I'm just going to click on one of these, just double click and open one of these studies. And now we have a series of measures that were taken by ultrasound. We've got aortic flow, long axis. These have been labeled by the user at the time of the acquisition, so LA meaning long axis. There's a couple of muscle measurements here, 3 of those, and then we've got SA for short axis. So I'm going to start by looking at the long axis view, so I double click on him, and there we have on the screen a freeze frame end diastole of the long axis view with the M mode line drawn through it. And then below it here you can see the M mode trace with time on the bottom axis and the dimension up the y-axis in millimeters, showing the cross section through the heart over time. You've got ECG and respiratory trace down here, and it's worth having a look at these briefly. If you can't see the ECG in green and the respiratory trace in yellow, go to View and make sure View ECG and View Respiration and View Physiology is turned on. Using the right mouse button you can increase the amplitude of the ECG trace, and using the left mouse button you can make it smaller, so it's worth making that big enough to see. And then respiratory trace, again, make it bigger by left and smaller by right. You can see here that the trace we have on the screen is between breaths, so it's actually a very good area to analyse. If your trace, for instance, I'm just scrolling back through, is this area here, you want to move out the way of that and find an area that contains a nice flat respiratory trace. What you don't want to do is include any measurements taken during any gulps of air, breathing in, etc., because it will distort the data. So how do we do the measurements? Very simple. Go to Tools and select Measurements, or press Alt-T-M on the keyboard, and you end up with the LVM mode or LVM editing window. It'll automatically select this because it pretty much assumes we're doing an LVM mode when you've chosen M mode. You can choose generic measurements and other such things. Looking at the data on the screen, this is a fairly clear picture. This is a young animal, and this is fairly usual for young animals to have a nice clear, discernible walls, endocardium here, very clear endocardial margin, a very clear margin here. You can see the papillary muscle, which is just in the image where I'm pointing the mouse now. The papillary muscle is very clear, and you can see the posterior wall motion nice and clearly. So we need to take some measurements. We're going to measure some wall thicknesses and internal dimension thicknesses. This wall up here is in fact the septal wall. It's an oblique angle through the septal wall. It's the same oblique angle we'll be taking in all of the animals that we measure using this method. So I'm going to choose up here IVS, which is interventricular septum at diastole. Choose a point, find the outside wall, click, drag, and then click again, and then automatically the software will determine we're going to measure internal dimensions, so we can then move back down to the endocardium on the inside here, click done, and we can move down to the edge of the heart and click again. So it's a nice easy just move and click. There's no dragging or anything going on, just click and it will close when you click it again. It's taken 3 measurements. If you do make a mistake, you can delete, or you can go back in afterwards, click with your mouse here, and you can move. You can see I can move that point and make sure they're in the correct place. And when you're learning this technique, it's worth going back and just checking that you're doing it right to start with. The next measurement we'll do is the same measurement, but this time at systole. So we choose IVS at systole, choose the top point, move down to the endocardium there, choose the maximum peak. You can see these lines run only vertically, you can't run them at an oblique angle. So if your peaks of systole in your top wall, the septal wall here, and your posterior wall don't quite line up, you can use a little dot you can see in the box here just to make sure you select the peak, and then you can go down and close that. There we are on the posterior wall. There we go. So those are our measurements. We've also got the other option with this software to measure or estimate the volumes in the heart. It does this using this long axis view, and by measuring the distances during diastole and systole along this M-mode line, it interpolates that, integrates it into a repeated barrel type measure. It doesn't take into account LV length at all, so if you do it, use it with caution, make sure that your LV lengths are similar in all your animals and you're not missing a trick, and that's where the 2D analysis comes into its own. But in a simple phenotypic study like this, you can do 1D analysis, click on LVID trace in the window here, and then you can basically click on all of the systolic peaks and diastolic troughs using your mouse. It joins the dots for you. I'd do 3 or 4 cycles just to make sure you've got them all. When you've reached the end of your uppermost wall, you can do the upper first or the bottom first, it makes no difference. When you get to the end, first of all you do a left mouse click, and then you do a right mouse click, then you move down to the bottom, left mouse click, and start again. That little right mouse click is really important. It closes one of the lines and allows you to start a new line. If you don't do that, you get all sorts of errors appearing on the screen, and you'll have to cancel and start that again. So when you've finished both walls, you finally right click, close the line, and there you have a series of numbers representing dimensions, estimated volume, stroke volume, ejection fraction, and fractional shortening, as well as cardiac output. I must reiterate, these are estimates. They are by no means determinants of cardiac function in any accurate sense, but you can use them as a comparison between mice or within a mouse and repeated measures. So please bear that in mind when you do any analysis on these, and certainly when you discuss these, you need to make sure that you're not being too literal when you talk about the numbers. But now we've finished the long axis view, we can close the measurements window, and by pressing F3 we go back and browse our file list, and we'll now choose short axis. Short axis measures, you can use the same measurements. So I've loaded the measurement window here using Alt-TM. You can use the same measurements you did in the long axis, with the exception of the LVID trace. It's not really applicable in short axis. You're not quite measuring the same bit, so it's safer just to use it in the long axis, or you can use it just in short axis, but certainly don't use it in both and take any averages just in case you skew your data the wrong way. So we will choose this time left anterior wall, because this time we're measuring up in here. You can see the anterior wall. This is the septal wall, here's the anterior wall. So we'll choose the anterior wall at diastole, and we'll do a quick measure of anterior wall thickness. The software again knows we're going through to internal dimensions, so we'll continue that through. We'll move them so we can see them. You don't have to move them, I just like to move them so I can see them. And then we'll do the anterior wall at systole, and again making sure you do not choose the papillary muscle, you just choose the peak of the wall. And when you've done those measurements, you can make sure they're looking good. It might be worth comparing these with the measurements you took from the long axis. So just let's get a little anterior wall at systole. That's posterior wall at systole, 0.98 millimeters, and it says posterior wall in brackets 2 because it's the second posterior wall measurement you've made. So 0.98. If I go back to browse and load the long axis, 1.04, so it's 0.2 millimeters different, which is pretty good. I like the ballparkness of that, so I'm happy with that. Finally, we go to aortic flow, load that file up. This is a pulse Doppler trace, and when you load the measurements window, you'll see that it loads up a pulse wave Doppler measurements, not the M-mode measurements. You'll also notice that the default is mitral valve. You can turn that default to other settings, but it's easy just to leave it on its default, and it comes up as mitral valve. So make sure you click on the drop down list and choose aortic valve, because this is clearly aortic flow. It is more than likely that at some point you'll be measuring pulmonary flow, mitral valve flow and other things, so don't remove it from the software by any means, but certainly make sure you've chosen aortic valve. We want to measure the peak velocity, so we click on AV peak velocity, and we can click on a couple of the peaks here just to get measures of peak velocity. I'm just going to choose 3 for the sake of argument here, and now we've got 3 measures of peak velocity. I'm just going to move them around so they're all slightly separate. There we are, and you can see they're all very similar. We also would be interested in looking at the VTI, the velocity time integral, so the integral of these curves. You can laboriously, if I click on this now, you can see if I click here, it'll do a kind of an auto trace. Ooh, there we are, over the top and down the other side, and you can see now if I right click, it will save that. It'll take a few seconds, it's just thinking about it. There we are. You can see it's a little bit dodgy. I would have to move a lot of these points to make this more accurate, so I'm going to delete him. There we are, right click and choose delete. You can, down here in this thing called real-time traces, you can show negative peaks. This is aortic flow, therefore it's downflow in the trace, therefore it's negative peaks. If you choose negative, you'll see the negative peaks. If I choose positive, you'll see it's chosen the positive peaks in green. So choose negative peaks, and now cleverly the VTI will follow these red lines. So by clicking just before a peak, clicking just after a peak, before a peak, after a peak, before a peak, and then finally after that peak, and then using the right mouse button, you can see what it's done is it's combined the red line with the blue line, and the blue line is traced through the red line. You'll notice I didn't include these little shoulders in the analysis. There's no real need to. To be honest, if you do include them, it really makes very little difference to your data, because the percentage of this to the rest of it is tiny. But to be complete, you don't want to include the shoulder, so make sure when you're clicking, you click at the start of this one and right at the end before the shoulder. That's when the aortic valve is just shut and there's a little bit of turbulence within the aorta there. So that's going to be the flow. This gives you an index of VTI. You can see here the number of VTI. It's in centimeters because of course it's integrated velocity, which is centimeters per second, so that's reduced it down to centimeters. It is, as I said before, in relation to stroke volume, so it's worth remembering this number, and maybe if you get some animals with some particularly high stroke volumes, just check they also have particular high VTIs, and you should be able to correlate these two numbers. So now we've got measures of aortic flow and some LV function in 2 axes. We can go back by pressing F3, which is browse, and we can see that the aortic flow long axis and short axis have now turned a lighter colour, and that implies that we've edited these data and we've edited the images, and we've therefore added some annotations. And you can see if you click on them, the annotations appear in the little thumbnail image down here. We've now got the option to browse not by just images but by measurements. If you click on measurements, you can see, just expand that a little bit, here we are, you can see all the measurements we've taken. These are actual measurements worked out from what we've done, and then below that we've got calculations, and these are derivatives of the measurements we've taken, like ejection fraction, aortic mean velocity, gradients, and masses of the LV, which are quite useful parameters to be able to analyze later. So make sure you've got numbers, make sure that everything's complete. You can then close the study by pressing F4 or clicking on the close study button. You want to commit the session data, makes it copied into the file, and you can see now you've got the data here, the analysis up on the screen, and you can see the thumbnails have the analysis. And now we want to export these data, the numbers of the data, in a spreadsheet format to be able to edit, annotate, analyze, and plot. So you can click on export, so you select the file you've just edited, or you can select by pressing shift all of the files here, but I've only edited one of them, so I'm just going to click on that, and I'm going to click on export. By default my computer saves it to the desktop, so do make sure you put it somewhere where you can find it. It's going to be a CSV file, a comma separated value file, which Excel should load by default. It's going to call it the name of the study, so the name of the study followed by the name of the animal, followed by the date the study was done and the time it was done, the person who did it, and then there's a gap at the end, so I may want to label this as week 5, which happened to be the week of this animal's life where we did this measurement. So that's week 5. It's going to be on the desktop, so I press OK, and there it's exported those data as a spreadsheet. Another tutorial will go into what those data all mean, but at the moment you've exported them, so you can carry on, do the next animal, do the analysis, and then export those data. So that's a brief summary, whistle-stop tour, as it were, of the one-dimensional cardiographic analysis using the Visual Sonics VEVO770.